So in the last class, we were looking at the conditional density of a Gaussian random vector. So let's look at the proof of that. Okay, proof. Okay, so essentially, I have to write the joint density of xy and divide it by the marginal to get the conditional, right? So now what will be the joint? So for example, if you have xy, two random vectors with the corresponding covariance given by kx, ky, kxy, and kxy transpose. I think something like this, right? So I think it should be a transpose. Yeah, it will be a transpose of this. Okay, so let me call this as something like B, C, C transpose D. Okay, so there are four matrices like this. So with this notation, let's get started. So what will be the joint density of xy? So if xy of xy would be exponential minus half times xy transpose. So that is x transpose y transpose, right? The okay times the covariance k inverse times x transpose y transpose whole transpose, right? So this is the exponent divided by 2 pi power the number of terms, right? So you have n plus m terms by 2 because x is of dimension n and y is of dimension m, right? Square root of determinant of k inverse. So is this okay? I mean, this is fine, right? Fine?
Yes, sir. Yes, sir.
Okay. So now I have to write the inverse of k, right? So how do you write the inverse of k? So what do you think is k inverse? So k inverse, I'll write. Okay, sorry, I think I made a mistake here. So let's use
Sir,
the k. Yes.
it should be determinant of K, not K inverse. Determinant of K inverse should not be there.
Determinant of k. That's correct. So yeah, this should be. Let me just think. Is this? Yeah, this is correct. Yeah, this should not be determinant of k inverse. Hmm? Okay. So okay, fine. So I'll write k inverse as BC transpose D. Okay. Is that fine? So if a matrix A is symmetric, A transpose is equal to A, then the inverse, if it exists, is also symmetric. Okay. So I'll call that inverse as this matrix BC transpose D. Is that fine? Of course, there is a way of finding.
Sir,
Yes.
sir, one question not related to this.
Uh,
Like, sir, in the previous lecture, you said that if any matrix is symmetric,
hmm.
sir, then
Yes.
is it necessary that it should be positive semi-definite?
Not necessary.
Okay. Or
Symmetric matrices need not be positive semi-definite. Hmm?
okay, sir,
So
in
there
the
is a,
inverse true. Like, if it is
huh?
positive semi-definite, then it will be symmetric.
No, not necessary.
Okay.
Even that is also not necessary. See, how do I put it? Yeah, you take a matrix, you can give always a counterexample, right? This is a matrix. It's not, okay, sorry, just do this. Is this symmetric? It's not symmetric,
Okay.
right? But if you multiply by xy, what do you get? You get y and 0. And then you have xy, right? So you get xy. So no, this is not symmetric. No, and not necessary. You can give us a counterexample. Okay,
Okay.
let's not worry about the counterexample now. You can give counterexample.
Okay.
Okay, so now I can write the exponent in the following way, right? So the exponent would be minus half, okay, x transpose y transpose k inverse. So k inverse is what? This matrix, right? A, B, C, B, C, C transpose D. So if I plug it in there, I get the following, okay, X transpose BX plus X transpose CY plus Y transpose C transpose X plus Y transpose dy. Okay, this would be the exponent. Do you agree? Fine. So now what is f of x given y, of x given y? This will be the of the form something like f of some phi of y, right? That is like f of xy divided by phi of y, this thing, and some other function here, right? So some function. This is the general form. Do you agree? So now, if you look at the this expression here, right? This expression, the exponent here, I can rewrite the exponent in a slightly different fashion. Okay, so for example, if you look at this term, right, y transpose dy, that is a function of y only, right? I can pull that out of the exponent and call it as phi of y. So now I can write this as some phi of y. We will see what phi of y is times we'll have the remaining, right? So what is the remaining? You'll have exponential of minus half times, right, x transpose bx plus x transpose cy plus y transpose c transpose x. Okay, this is what we have. Okay, is that fine? Fine? Fine, right?
Yeah. Yes, sir.
Okay,
Yes.
yeah. So now I'll just complete the squares in the exponent to get the following. Okay, so again, I can write this as p of y. Okay, exponential of minus half. I can complete the square as follows. So I can write this as x plus, okay, so b inverse c y whole transpose, right, this into this whole thing into x plus b inverse cy, okay, plus this will be plus y transpose c transpose b inverse cy. Okay, this is something, this is how I can complete the square. Okay. Okay, now again once you complete the square, again you can observe that this term is independent of x, so we can just pull that out and absorb into phi of y. Okay, so now what is it that you have gotten? So we need to describe this by a mean and covariance, right? So what should be the covariance and what would be the mean, right? So I think I missed the okay, sorry, this there is a b here, okay, in between the b. Okay, so now I can write this as follows, right? This is some phi of y. Let me call this as phi dash of y. Okay, exponential of minus half. Okay, now I can write this as x plus b inverse cy transpose this thing. Okay, of course there are constants, for example divided by 2 pi power something, all that. So I have observed that into phi dash of y, so this depends only on y. Now if you look at f of xy of xy, I can write this as f y x given y of x given y into fy of y, right? So now this is only a function of y, and this is something that depends on both an x and y. And all that we have to care about is the exponent of this. The moment I know the exponent, essentially I'll know what the distribution is, right? By observation, what can you say about the mean and the variance or the covariance of this thing? F of x given y. So the mean is B inverse. This is minus B inverse Cy is the, sorry, not y. Cy is the mean. What will be the covariance? Covariance is B inverse, right? Because x minus mu whole transpose K inverse times x minus mu is the exponent of a Gaussian random vector with mean vector mu and covariance K. So by that observation, I can write the conditional density as Gaussian with this mean and the covariance. Okay, so it's mostly algebra. That's what you end up doing. So what can you say from this? So essentially, it says conditioned on y, right? Conditioned on y, x is Gaussian with mean B inverse Cy and covariance B inverse, right? So that means I can write x as, okay, conditioned on y equal to this y, one part is fixed, and you should have a mean of, let me write it like this. Okay, now I have to see what G is. Conditioned on y, right? So this should be Gaussian. We should have a zero mean, because when you say expected value of x given y, I should get B inverse Cy. So given y, this is a constant. G should be minus B inverse C. Okay, that will be G. Okay, so what will be the covariance? The covariance of this would be B inverse. So the covariance of this V should also be B inverse, because I'm subtracting. When you look at the covariance of x given y, you have to subtract the conditional mean from x and multiply it with the transpose to get and expected value to get the covariance. So the covariance will be this. So in general, if you have jointly Gaussian xy with certain joint covariance, I can write the relation. I can write x and y through this relationship. Okay. Is this fine? Any questions? Are you guys there, or did I?
Yes, sir.
Okay. Any questions?
Sir, here the covariance of G is I, right?
No, G is a matrix. It's a constant, right? G equal to
So, okay.
this. V is Gaussian. Think of it as a noise. Okay. Fine. Okay. So why is this useful? For example, I can tell you. Suppose if you have xy as jointly Gaussian, and if I want to find, so something like this, right? Y equal to h x plus w, right? I want to find an estimate of h given what I know x. So that expectation would be that estimate of h hat would be expected value of, what is h hat? h given y equal to the observation, right? So this will turn out to be an MMSE estimate. So now if I know the joint distribution of h and y, right, turned out to be Gaussian with certain covariance, then h given y conditional distribution will also be Gaussian with certain mean and covariance, which can be found using these expressions. And now the expected value of that is one of the term like this, B inverse Cy. Okay, so essentially it turns out h hat is, in this case, is some constant a or some constant matrix A times y. That will be your estimate, MMSE estimate of h. Okay, so we will see this a little later maybe, but just to give you a quick reason of why we need to look at all this in the context of, for example, signal processing or communications, this is the reason. Okay, so now let's look at